so okay, let's do page 35. Let's go to page 35. Okay, so we've talked about power rule and how in order for us to do power rule, we have to have a couple of restrictions or a couple of things in place, right? We can't have terms with parentheses, radicals, even converted to rationals. But here, now we're going to talk about problems where there are parentheses in place, and we can actually find the derivative if there's parentheses involved. So first, we start off with something called product rule. This is formula used to find the derivative, again, slow formula, for products of two or more functions. So if I have two expressions that I want to leave in those two separate locations, I can find the derivative, and the process is called product rule. So let's say there is an f and a g expression portion of my problem. Now, if I want to find the derivative of two things being multiplied, I am going to involve both their derivatives, but it's not quite as simple as just f prime times g prime. Okay, it's part of it, but it's not the whole thing. So if I want to find the full slope formula for an expression that is separate as f and g, I need to go through this process called product rule. And the pattern is going to be the first function's derivative times the second, plus the second's original times the first derivative. Okay, so we call it f prime g plus fg prime. Okay. F prime just means you take the derivative, the g, whatever the second expression is, you leave alone, plus first expression, you leave alone, and second, you take the derivative. Right. So let's look at example 1 here. Y equals 3x minus 2x squared times 5 plus 4x. Now, this is one of those problems where if you wanted to, you could FOIL all this out, right? Expand all this out and just rely on power rule. But we're going to practice with product rule because there are times when we're kind of stuck in this spot where we can't FOIL out because of the rules that, you know, or we don't have enough rules or method to be able to expand. So if we can't expand, we're kind of forced into product rule. But here we could expand, but we're going to just practice going through product rule. Okay, so I'm going to, whatever comes first, I'm going to go ahead and label that as my f. Whatever comes second, I'll label that as my g function. I want to find dy dx. Again, that just means y prime. Dy dx means f prime of x. It just means find the first derivative. Okay, so I'm going to say dy dx equals, and I'm going to label exactly what I'm going to be looking for. So I'm going to label this f prime times g plus f times g prime. So we're just kind of taking turns and pairing up a derivative and the other term's expression. Okay, so 3x minus 2x squared, this is my, I'm going to label that as my f. I'm going to assign f prime. So what's the derivative of 3x minus 2x squared? Yeah, so 3x becomes 3. That's just linear. All degrees drop by 1. And then minus 2x squared becomes minus 4x. All right, we go through power rule. We bring the exponent down, subtract 1 from the exponent. I'll leave that in a set of parentheses. Okay, times the original g function. So what do I do there? Yeah, don't do it. Don't make any changes. Just bring down that 5 plus 4. Okay. Back to f. Yeah, the original expression here. G prime. Good. 5 goes away to a 0. 4x becomes 4. So this is my derivative. I could
do power rule.
Huh?
Do you power rules?
We did, yeah, we did power rule. So the 5 is a constant, so 5 goes to 0, and the 4x is linear, so the x drops out, just the 4. So we have the derivative. I mean, we could FOIL this out and clean this up, but this is the slope formula for whatever this graph looks like. Okay. So just remember that anytime I have two expressions and I want to leave them as separate terms, I got to go through product rule, even though it feels like a lot of students just want to do this. Say, okay, well, that derivative is 3 minus 4x. And this derivative is 4, and then why can't that be the derivative, right? That's a lot cleaner, a lot simpler, but that doesn't work out, okay? Now, if it was 3x minus 2x squared plus 5 plus 4x, if these are nicely separated with no parentheses and everything is just added together, then I can go ahead and take them separately. But because they're connected by multiplication, we have to go through this product rule if we want to leave it in this form. Okay, so we can't do this. Okay. Okay. We also have something called quotient rule. And you can imagine what this is. This is where if I have two expressions that are being divided by one another, and formula for finding derivative of a function that is the quotient of two other functions. So if there's a numerator denominator portion that I'm unable to clean up in any other way, and I have to leave it in that form, I go through quotient rule. Now, quotient rule is going to feel a lot like product rule at the top. Instead of f prime g plus fg prime, it's going to be f prime g minus fg prime. So the only change in the numerator is, well, at the beginning, it's just that sign in between. But it's more than that. We can't just stop there and just say, okay, it's just changing that sign from product rule. There's also a denominator portion. We also have to make sure whatever the original denominator is showing, we're going to take that entire denominator and we have to square it.
So like for first one, you just leave it like that.
Yes, for now, yeah, you can leave it like this. Now, we're going to be asking something more a little bit later, and so we may have to expand this out and clean it up and look for something else. But technically, this is the right answer because it's an unsimplified form, but it is correctly, it's the same answer. It's the right answer. But if I asked you, if I were to expect you to simplify, I will make sure to make clear that. But if you want to simplify this, you could FOIL this out and combine like terms. I'm just skipping that step. Okay. Now, if you look at example 2 here, 3x minus 2x squared over 5 plus 4x. This denominator, we are unable to split this up into individual fractions. So do you remember when we talked about how if we see a messy denominator, we're able to separate into individual fractions and clean it up that way? Yeah.
Oh, yeah. That.
Right. Much like this term, right?
When in the first.
Right. When we do with power rule, where I said, okay, that denominator is getting in the way. Let's just go ahead and split up into individual fractions and then clean up and bring it up. That we can do if there's only one single term sitting below. But if there's more than one term, we're kind of stuck. We can't bring it up, but it's not going to make it any cleaner and easier. And that's a different rule that we're going to learn later. But if there's more than one term and they're added or subtracted by one another, we're kind of forced in this fractional relationship. It's not easy to split up and get rid of that fraction. So because we're stuck in this form, we're asked to find the derivative. We're going to go through something called quotient rule. So quotient rule is your denominator and numerator cannot be changed into a different form, but we are asking for the derivative. So quotient rule. Okay, I'm going to label exactly what we're looking for here. So see if you're able to fill the rest of it in based off of what f and g are defined and what quotient rule is asking for you to find in each piece, in each part. Okay, so f prime, same f prime as with product rule, g minus f g prime. But because we're doing quotient rule, a lot of students do forget about this denominator portion. So just keep in mind that quotient rule does have that denominator portion that product rule does not. Okay. And if we wanted to clean this up, we could FOIL all this out, but I'm going to skip that step. But if you want to FOIL this out, you have to go through. Yep. Well, you've got to clean this up. You got to go through and expand this way. What we cannot do is we can't do this. We can't say, oh, there's a 5 plus 4x here. I'm going to take one of these out. Why can I not do that algebraically?
Because the square is different function there.
Something else. Something is preventing us from doing it.
The 3 minus 4x. No, right?
No. If it was just right. If it was just this, if it was just that without that second term, we could cancel this out. But we can't cancel out if there's this second expression here. And why is it again?
It's the minus sign.
That minus sign. Yeah. Anytime there's any attachment with addition or subtraction, we're kind of forced into leaving it alone. It's not easy to cancel across addition and subtraction. And if we do, it's going to mess things up. So now if it was everything multiplication, then yeah, that's fine. You can take that out and clean that up and take out one of the 5 plus 4x's, but we cannot do it unless we are able to somehow resolve it. Or as Eugene said, if we can somehow factor a 5 plus 4x from both those expressions, then we can take a 5 plus 4x out. Okay. This looks messy, but it does the same thing as other derivatives. This just describes the slope behavior of the original function. So we're going to learn more and more complex derivative rules, but I don't want us to lose sight of the fact that it's doing all the same things as other derivatives. It's just telling us the slope of some other graph. Okay. Of the original graph that we're starting with. Okay. All right. We're going to definitely do some more practice with product and quotient rule. But I want to talk about some notations here. And let's go to page 136. Okay, so higher order derivatives. Sometimes you are asked to, usually we don't go past the second derivative. Usually it's just y prime, y double prime, like particle motion, right? We have position, velocity, acceleration. Typically we don't go past the second derivative, but sometimes you may be asked to go past it if for expressions that clean up nicely, okay? So sometimes you may be asked to go up to a fourth derivative, but typically there are derivatives that just get simpler as we keep going. I want to just kind of show you that we could go past the second derivative and it doesn't feel very difficult if we have nice polynomials here. Okay, so let's find y prime first. Y prime, we go through a power rule for each term. Every term is set up and ready. There's no radicals. There's no variable in the denominator. No parentheses. Okay, so what's the first term become?
2x to the fifth.
Yeah, 2x to the fifth becomes 10x to the fourth, right? We deal with the power rule. We bring the exponent down in front, and we subtract 1 from the exponent. Okay, 4x x to the fourth becomes
4x.
third. Yep, we subtract 1 from the exponent minus.
Almost in 7.
What's the next one?
Yeah, 6. 9x in seconds.
Yeah, we'll bring the 3 down, multiply with the 3 in front, 9x squared minus 16x plus 10. What happens to the minus 12?
0.
0. Okay. So you see, if as long as I have nice positive exponents, all my degrees will just do what?
Decrease by 1.
Decrease by 1, right? And then any constant will just drop out. Right? So now if I want to find y double prime, keep going.
40x in there.
Okay, plus. Okay. Minus
18.
minus
16.
16. So we see that linear becomes constants, which goes to 0. Right? Keep going. Mhm. Mhm.
18 minus 18.
Okay. Now, why is there a decreased number of terms? Like we started with this many, but then we seem to be decreasing here.
Is the constants control.
Yeah, because the more that we find the derivative, every degree is going to drop, and eventually it's going to become a constant. Eventually, it'll go to 0, right? Okay. One more here. Fourth derivative.
40x plus 24.
It's 120 times 2 here. 240. Okay, 240x. Yeah.
So, I mean,
But then if I keep finding the derivative, what's eventually going to happen?
it's gonna be all be 0.
I'll be 0, right? So that's not the case for every function, but if you have a nice polynomial like this, if you find the derivative enough times, everything will eventually go down to 0. And that's just a nice property with polynomials here. Your derivative are going to, in a sense, kind of behave nicely. They're going to clean up nicely. Other functions are not quite like that, where every derivative is potentially getting more and more complicated looking. But the nice thing about polynomials, your derivative will get simpler and simpler looking.
What's the purpose of doing that? Like to do it like 4 times still.
We're really not going to see a good application for this in this course, but for BC calculus, we do use these derivatives to help us model a different type of function that's harder to find the derivative for. So polynomials can be used to mimic or imitate other functions that have a harder time with derivatives. But I mean, past the second and third derivative, it just means to find the rate of change of the function above it. I mean, we do see application with position, velocity, acceleration, but the third derivative, as far as something that's application-wise for us, we're not going to see a whole lot with that. Okay. All right, notations. I talked about how there's a lot of different notations for first derivative. You could see f could become f prime, g could become g prime, y could become y prime, dy dx. They all represent derivative. You could even say y prime of x, or even f prime. These are all just notations that represent derivatives. So just have to kind of get used to. Basically, anything that is prime is going to be derivative. There's also this dy dx, which means find the derivative of my dependent variable y with respect to x, and that means the same thing. Notation for second derivative, you can imagine just add another prime there, f double prime, y double prime of x, y double prime. And also this notation here, d2y over dx2, this means the second derivative. This doesn't mean, oh, I'm going to square the first derivative. This just means this is a notation. I'm not going to really do anything. That's not an exponent per se. That's the notation for second derivative. So whenever you see that d2y over dx2, that just means find the second derivative. And then this is less common. We're not going to see a whole lot with third derivative, but you can just kind of tack on that pattern and form the notation for third derivative. Okay. Okay, there's not a whole lot with product and quotient rule, just having a matter of being able to practice that. So let me see though. I think maybe I can pick out some problems from page 41. These are product and quotient practice problems, and I figure we can kind of just see these process in action within a problem here. So it says, number 1, page 41, what is the instantaneous rate of change at x equals -2 of the function f of x? Now, what is this asking for, you think? What is the instantaneous rate of change? Derivative at, yeah, so we're basically looking for f prime of -2. That's our goal, right? Our goal is to find f prime of -2. So we're going to find f prime of x first. After we find f prime of x, we know that we have our slope formula. And this is just asking, what is the slope of this graph that we don't see at this particular point? So we're going to build the derivative, and from the derivative, we can plug in -2. Okay, so but if I want to find the derivative, so we don't worry about the -2 first, just f prime of x. If we want to find f prime, guess what rule we have to involve here?
Derivative. We have power rule. So
Yeah, power rules involved, but what do you notice about the form of this function here? Quotient rule. You see the numerator and denominator. Now there's more than one term in the denominator. If it was x minus 1 over x squared, I would go ahead and split up into individual fractions, clean up. But here, that +2 kind of forces us in that numerator and denominator. We're stuck in this form. It's hard to get out of it. We're going to have to go through a quotient rule. Okay, so let me remind us our quotient rule here. Okay, we're going to have to work towards memorizing this rule here. F prime g minus fg prime all over g squared.
do you want to just show some like quiz?
No, I won't give it to you. Yeah, we have to memorize it. Yeah. Okay, so I know there's a duplicate variable there. This f to f prime, it just indicates I'm going to find the derivative, but then within the notation, I'm going to indicate f and g as numerator denominator. So I'm going to label everything here.
You leave it open in the G. So
Oh, sorry, thank you. Okay, so let's build our derivative here. F is my numerator, denominator is my x squared plus 1. So what's x minus 1's derivative? Just 1, yep, x goes to 1, 1 goes to 0. G function, no changes. Back to f.
X1.
Mm-hmm. G prime.
X.
More than x, 2x, right? Yeah, bring the 2 down. All over. Yeah, so we got to take that entire denominator, running on a room here, x squared plus 2 quantity squared. So I got to take my entire denominator, I have to square that whole thing. Okay, I know it looks messy, but that is the process to find the derivative. Let me just do some cleanup before I actually plug in the -2. Feels a little bit cleaner here. I'm going to distribute the 2x through here, minus 2x squared. Again, we can't do this. I know this is going to feel tempting here. You're going to feel like, okay, I can just get this a lot cleaned up faster if I just take out one of the x squared plus 1, but I cannot do that. Not with quotient rule. You have to spend the time to actually FOIL. If you want to clean it up, you got to distribute, FOIL this out. So if I took the -2x there and I just distributed through, so I got -2x squared plus 2x. Clean this up here, I get -x squared. Oh, sorry, you're right. I messed up. 2. Okay, so this is my slope formula. Any x value I plug in, I'll get a number, and that number will tell me how steep this graph is at that particular point. Okay, so now what's my last step here? Plug in the -2, right? Plug in -2 in for x, and I can give it the location. In return, it'll tell me the slope. I messed up somewhere here.
Oh, it's 6 squared on the bottom line instead of 8 squared.
Four, yeah, sorry, making all these mistakes. Sorry, 6 squared. 4 plus 2 is 6. 6 squared is 36. Okay, questions? Okay, number 2, it says an equation of the tangent line to the graph at point 3, 4 is. So this is just one step beyond number 1. Okay. Here I have the slope. If I want to find the ordered pair, I will plug in and find the y value. And from there, I'll do point slope form. Y minus y1 equals x minus x1. So if I want to find the equation of the tangent line, I'm going to find the slope. To find the slope, I want to find the derivative. So guess what? We have to go through again if I want to find the derivative. Yeah, go quotient rule, right? After I find the derivative, what can I do? How can I find the slope from there?
Plug in the plug.
Plug in what?
3.
Well, all it needs is what?
3.
Just a 3, yeah. Your derivative, this is a function. Your function will not produce any y variables, and it will only require the 3. Yeah. So we go through quotient rule, plug in the 3 into the derivative, get the slope. Once you get our slope, then point slope form. Okay, what's f prime here? 5. Okay, g is just the original, sorry, I'm messing up. G is just the original denominator here, 3x minus 6. Yeah, that will be for g prime.
Yeah.
Back to f, 5x minus 3.
Those give me the same formula.
If it's quotient rule, yes. If you realize there's a numerator and denominator and you cannot get out of that form, then to find the derivative, it's always going to be quotient rule. Yeah. Okay, let me do some cleanup here. Distribute the 5 through. Distribute the -3 through. Well, I say -3 here because it's easier if I just have that 3 in front here and I just pretend like it's -3 and then just distribute it all at once. Okay, so here that's nice having the 15x's canceled out. -31 plus 9 is -21. So what can I now do with that derivative?
Plug in the 3.
Yeah, plug in the 3, yeah. Okay, we plug in the 3, we get -21 over 9, which is -7/3. We take that ordered pair and our slope, we put in a point slope form. Now this one is in general form, or standard form. And to get to that form, we have to get rid of the fraction. I'm not going to ask you to go beyond this step. But if you were to go beyond this step, if it was like multiple choice, for instance, on the AP exam, you could just distribute everything through by a 3 to get rid of that denominator. Distribute everything through by a 3, and that will get you to whole number integer values and just rearrange it. Eventually it'll match up with. But point slope form for us is usually going to be the best bet here.
But I have a question.
Yeah.
Why would anyone need to get rid of the denominator fraction?
Just because if you look at our answer choices here, they don't have any fractions showing. So to make it so that it's easier to know what this is the same thing as, in terms of the expression here, if I just multiply everything through by 3, that will get rid of that fraction. It'll make it easier for me to compare my results.
So like they're always gonna ask you to get rid of that fraction.
It depends. So yeah, I mean, if it was free response, I would leave it in this form. But if it's multiple choice, you know, their answer choice could be point slope form. It could be standard form. You just have to kind of know how to get from your version of the answer sometimes to their version. Okay, I think there's some good practice here that we can do here. So if we can look at number 5, we're now going to see some variety of different methods here. So everyone good with 1 and 2? Okay, so here's number 5. Number 5 says d of dt of t squared minus 1 over t squared plus 1 over t at t equals 2 is. Do you guys know what this is asking for?
Rate of change.
Okay, what's another word for that?
Derivative.
Yeah, find the derivative of this function, what? At 2. Yeah, so imagine this was y of t. Right, and the t is just a variable instead of x, and this d over dt just means find the derivative of this expression. That's all it means. Okay? And it's not naming this function, but you know, if you want to make it so that it feels more consistent with everything else, we can call this y of t. And ultimately, this is asking for find y prime of 2. Right, find the slope, find the derivative, and find the slope of this graph at 2, whatever that graph looks like. Now, look at how this is set up here. What rule can we use to get to our derivative? Power rule.
Oh, not probably.
No need for product, no need for quotient. I mean, we could do quotient, but again, quotient is one of those things where if you can avoid it, you prefer to avoid it because it's so cumbersome with the f prime g minus f g prime all over g squared. This one, we can actually avoid quotient rule entirely because every term, every variable can be put where?
In the denominator.
Well, it's in the denominator right now, but they can all be put where? In the numerator, right? Because there's not more than one term. If it was t plus 1 or t squared plus 2 in the denominator, we're stuck. But that t squared and t can be brought up to the top.
Negative t negative 2.
Right. So y of t is equal to t squared minus t to the negative 2 plus t to the negative 1. If you look, every term is nicely set up. We can avoid quotient rule. We can just do power rule 3 times, get to our derivative, plug in the 2, and then we should be able to get down to our slope. Okay, so let's try y prime. Okay, t squared becomes 2t minus what is a t to negative 2 become?
Minus 2t.
Minus 2t, what?
Negative 1 power.
Remember, we have to always do what after we bring down the exponent?
Minus.
Subtract 1. Yep. So 2t to the negative. What's negative 2 minus 1? Negative 3. Yep. Okay. Next term.
Minus t. Minus t minus 2.
Yeah, I know. I think the tendency is we see that -1 and we think, okay, let's just go to 0, but we got to subtract 1, right? So it's not always going to be what you could potentially expect. Yeah, so -2.
If you bought the like the
Oh, did I mess up here?
yeah,
Minus
yeah, wouldn't you? I'm
2.
confused about something like if you brought the -2 down, wouldn't it like cancel out the minus sign and be a positive? That makes sense.
Yes, hold on. 2t, you're right. So when this negative comes down, yep, the two negatives cancel out, that becomes positive. Are we good with the derivative here? Okay, so I'm going to do some cleanup here. Y prime before I plug in. Just feels a little bit easier. Okay, let's talk about this. If I were to clean this up, how would this look? If I were to get rid of that negative exponent.
6.
1/2t.
So yeah, I want to say that the t to -3 comes down, but the 2 stays up top. Okay, so the 2 is not attached in a way where it has to come down with the t, and we don't want it to, right? The -3 only impacts the t, not the 2. So 2/t³ minus, okay, now what does this become? Minus
2.
How can I rewrite this without the negative exponent? Good, 1/t². The t² comes below, but there's still a number up top. It's a 1. Okay, it's a 1 that comes down.
You plug it in.
Yeah, so now we can plug in the 2. Good. Now we want to find the slope, whatever this graph looks like. We want to find the slope of this graph at 2, and this is how we're going to find that slope value. Two over 8 is same thing as 1/4 minus 1/4. Y prime of 2 is just going to reduce to what? 4. Okay, number 6 on the back. This is a particle motion problem here. Okay, it says the position of an object moving along a straight line is given by S of t. What is the acceleration of the object when t equals 2? So S of t is position. How can I make my way down to the acceleration function?
There's like those functions we learned.
Yeah, so you know position's first derivative will take you to velocity, and the velocity's derivative will take me to. Right, so second derivative. Oh, sorry about that, guys. Wait, it's shortened because of what?
Yeah, we're set.
Got it. Sorry about that.
I think tomorrow that. We're doing math. Yeah, it's like not for
Yeah, very appreciate it. Thank you.
Do you have to do 29?
No, you didn't. I just forgot.